All right, we're going to get started on section 8.2. The title of this section is Primitive Roots of Primes. In fact, in this section and the next section, we're going to determine all those integers. They have primitive roots. It's going to be actually a limited number. There are infinitely many, but there are, comparison-wise, there are, few, basically. So in this section, we're going to actually show that every prime has a primitive root. And to accomplish this, we need to get started with something maybe looks unrelated. And this one is review some concepts related to polynomial congruence equations. We have seen some of this earlier in chapter 4. And then we're going to actually state and prove the main theorem concerning the number of solutions to a polynomial congruence equation. This is called Lagrange's theorem. And then as a corollary to this, we're going to prove give another proof for Wilson's theorem that we studied back in chapter 5. Then we're going to follow this by the two main results, actually, which concerning the title of this section is the existence of primitive roots. To accomplish this, we're going to prove theorem 8.6, which is going to give us the number of integers of a given order, and the order or those are the divisors of b minus 1. We're going to find actually a formula how many of a given order. And then we're going to end by showing that actually it's going to follow as a corollary the existence of primitive roots of primes. All right, so let's get started on polynomial congruences. So we're going to start by a definition. Let f of x be a polynomial of whatever degree with integral or integer coefficient. By a polynomial congruence equation, modulo a positive integer m. I would like this to be bigger than 1. We mean a congruence relation of this form. It's like still we call it actually a congruence equation, even it is actually more appropriately called congruence relation. So f of x congruent 0 mod. All right, so whenever we talk about equations in general, we are interested in what do we mean by a solution. A solution to the congruence equation f x equal to 0 mod m. Maybe we should say by a solution, maybe a better. By a solution to this congruence equation, we mean an integer r whatever kind of integer, such that f of r comes congruent to 0 on n. That is, it satisfies satisfy the congruence relation. When we substitute for x in the congruence equation, it becomes actually the actual congruence relation, means the congruence relation holds. All right. As we know that if two integers are congruent to each other, and one is a solution, or we also use the word root, okay? We call a solution or a root of the congruence equation. Then any two congruent numbers mod m, they actually will be solutions. So I want to put this in a form of a remark. If R is a solution or a root, sometimes I use both of these terminologies, okay? And R prime is an integer that is congruent to R mod m, then R prime is also a solution. And this is not very hard to show because, R prime congruent to R mod m. Back in chapter 4, we see that then squares, multiples of these with fixed numbers, and so on, all satisfy this congruence relation, and in general for any polynomial. So if we take R prime is congruent to f of R, but f of R is congruent to 0 mod m because R is a solution. So this implies that R prime is a solution. So in general, when we're going to consider solutions that of course are congruent to each other, we don't want to think of these are actually distinct or different, even though they are different as integers, but they are a solution, we're going to count them as one. All right? So in other words, for a solution for a congruence equation, we look at those integers in a complete residue system. All right, for the integer m or mod m, and the distinct one, because in a complete residue system, those integers are all incongruent, okay, mod m. So how many of these actually will be solutions? All right, so this is first thing. Let's look at another definition, very important for our consideration, that is the degree of a congruence polynomial equation. So here is by the degree of a polynomial congruence equation, or actually even polynomial, okay, f of x with the c mod m, we mean the highest exponent of x and f of x, where the coefficient or with coefficient not congruent or incongruent to 0 mod f. This is the word incongruent. To 0 mod. So in other words, that is, if we have f of x is equal an xn up to a sub 0, where all these ai's are integers, the degree of f of x is n, provided that the a sub n is not congruent to 0 mod n. And this is equivalently saying that m does not divide a sub n. Right? So the highest exponent then at the degree of this is equal to the highest exponent. All right, let's look at an example just to illustrate this idea. So the concept of degree is going to be different than that of a regular polynomial. For example, when we look at this polynomial, for example, take f of x equal 6x to the third plus x squared plus a. So the degree of f of x equal to 0 mod 5 is 3. However, the degree of f of x congruent to 0 mod 3 is 2. Because the first term, when we talk about mod 3, that it is actually 6. Here, since 6 is congruent to 0 mod 3. So in other words, basically mod 3, this term is non-existent. Okay, or in other words, to put it differently, that f of x becomes congruent to x squared plus a mod 3. So it is actually of degree 2. But also, polynomial congruences, there are some similarities to their solutions to regular polynomial equations. We know that there are some polynomial equations that has no solutions, and some they have the maximum number of solutions, which is equal to the degree, of course, counting multiplicities. And in general, either a polynomial, and it depends, of course, when we talk about a polynomial equation, solution over, what type of numbers are left. Means are they going to be real numbers, complex numbers, integers, and so on. So the situation there is varies, but in our case, because we are interested only in integer solution, the situation is, I don't know if it's easier or more complicated, but here's what it is. So let's look at an example. So if you take this x squared plus 2 congruent to 0 mod 5, and one way, of course, to check the solution is by taking a complete residue system mod 5. You could take the least positive one or non-negative 1, 0 up to 4, and check it in here to see if any of these numbers will satisfy this congruence. You're going to find that has no solution. Now, this is not because x squared is congruent to negative 2. It's like in actual equations, algebraic equations. Just simply because none of these numbers actually satisfy this. On the other hand, if you take this polynomial, actually minus 1 congruent to 0 mod p, where p is a prime, this has p minus 1 incongruent solution mod p. And this follows from Fermat's theorem. So Fermat's theorem says that for any x relatively prime, for any integer x relatively prime to p, we have x to the p minus 1 is congruent to 1 mod p. And of course, this is equivalent to say that x p minus 1 minus 1 is congruent to 0 mod. But among all these integers, of course, when we take a complete residue system, so if we want to find the incongruent solutions, the incongruent solution, to count them, they are going to be 1, 2, up to p minus 1. So these are the solutions, or what we call the incongruent solutions mod p. All right? So these are, in other words, the number of them is p minus 1. All right. Next, we come to the main theorem that will be needed for our purposes. Here's Lagrange's theorem, which tells us the number of incongruent solutions. It doesn't give us an exact count, but it gives us in a form of an upper bound it gives. So this is theorem 8.5. And for Lagrange's theorem. Of course, Lagrange has many theorems under his name, but since we know what the underlying idea is concerning congruence equation, so it must be that. So if we want to have, this is called Lagrange's theorem for number of solution of congruence equations. All right, so let's go ahead and state this theorem. Let p be a prime, and and f of x equal an xn plus a sub 0 be a polynomial with integer coefficients of degree n mod p. Okay, again, this is equivalent to saying that a n is not congruent to 0 mod p. And we could also say p does not divide a sub n. And we want, of course, the n in here to be bigger than or equal to 1. So we don't want it to be equal to 0 because it's a constant polynomial. That's not even very interesting. All right, then the congruence equation f of x congruent to 0 mod b has at most an incongruent solution mod p. Right, so give us the at most, all right? So there's at most this incongruent solution. The proof of this we're going to do by induction on the degree of the polynomial. And the degree of f of x, of course, mod p. So let's just start with the base step. For n equal 1, the polynomial is going to be a1x plus a sub 0. And then we have also p does not divide a1. And this implies that the greatest common divisor of p a1 is going to be 1. So it's going to be relatively prime. And this implies that the equation, the congruence equation, a1x plus a sub 0 congruent to 0 mod p. This is linear, okay, it's linear. And we did study these back in chapter 4, and we have a theorem. Let me see which theorem is this. By theorem 4.7. This equation has a unique solution. First of all, it has a solution because the greatest common divisor of A1, and which is the leading coefficient, or the coefficient of x, and the modulus, which is a prime, is 1. So by theorem 4.7, since greatest common divisor P1 is equal to 1, and this divides the minus a sub 0. Because we're supposed to write there to fit that theorem. This one is a1x is congruent minus a sub 0 mod p. This is the b in that theorem. So it divides this one. This implies the congruence equation has a unique solution. Has a unique solution, and this means that and the theorem holds. And the theorem holds for any. But in this case, it has exactly. So at most one, yes, it's true. All right. Now we're going to assume that the theorem is true for any for polynomials of degree k for some k bigger than or equal to. So this is our inductive hypothesis, induction hypothesis. We're going to assume that the theorem holds for polynomials of degree k. For some k bigger than or equal to. And then we're going to consider that f of x is a polynomial of degree k plus. Now, so we're going to consider this congruence equation. F of x congruent to 0 on t. In general, any equation either has a solution or has no solution. Then either the equation has no solution or has at least one solution. Well, if it has no solution, f of x equal to 0 more p has no solution, then we are done. Because the number of solution is 0, and 0, when we say that at most, all right, have n k plus 1 in this case, and it's, it satisfies, of course, this condition, no solution. All right, so let's assume that there is at least one solution. So assume that f of x for the equation has at least one solution. The equation has at least one solution. Let's say all right. So this means that f of a is going to be congruent to 0 mod t. Now I'm going to use a result from what we call the division algorithm for polynomials, which is sort of similar to that, where the ordinary equations that if you have a solution, then x minus a is a factor, all right, of the polynomial. This actually follows from the division algorithm for polynomials, and the proof of it is actually very, very similar to the proof of the division algorithm for integers. Yeah, this usually done in courses in algebra. I do this one in ring theory, field theory, so those courses. We prove this in a more general setting, but at least for polynomials with integral coefficient, of course, it is simple. So we're going to say that by the division algorithm of polynomials, we can write that f of x is equal to x minus a, the cube of x plus r, where q of x is a polynomial of degree less than or equal to k, all right? Because maybe some of the coefficients might actually be equal to 0, okay, congruent to 0 mod p. And r, which is the remainder, is an integer. Because we are basically dividing f of x by x minus a, all right? So we're getting this. In fact, to tell you the truth, that the q of x is of degree actually equal to k. Equal to k. Because when we are dividing by x minus a, so we're going to get actually the highest coefficient in here to be the an minus 1. All right? So equal to k. Now, let's substitute for f of a. So this is equal a minus a, the cube of a plus r. Now, when we take this is, and this is equal to r, and we're going to do this one congruent to, because this one is congruent to 0, mod p, then r is congruent to 0 mod p. Okay, so this one is since f of a is congruent to 0 mod p, because it's a solution, all right? So this r becomes this one. So now this implies that this equation, f of x, congruent to 0 mod p, is equivalent to x minus a, the cube of x, congruent to 0 mod p. Now let's assume that we have another root, that x equal b be another solution to f of x congruent to 0 mod p, and b is not congruent to that. It's a different solution, mod p, an incongruent solution. By the way, yes, here we also could say still f of x in here, so this is the same as f of x. It's just written in a different way. All right. So again, this is being a solution. This implies that f of b is going to be congruent to 0 mod p. This holds. Now let's go back to the factored form of f of x. So from here, this implies f of b which is, let me put congruent in here, x b minus a q of b. This is congruent to 0 because f of b is congruent to 0 on. Well, I know that since p is not congruent to a mod p, this implies b minus a is not congruent to 0 mod p. And this implies that p does not divide. And this also implies that the greatest common divisor of p and p minus a is equal to 1. So let's consider this congruence relation. B minus a, the q of b is congruent to 0 mod p. Now, since we have the greatest common divisor of p, the modulus and the coefficient in here, or this number, is relatively prime, I can divide by b minus a, because basically this means it's not 0, okay? So you can divide by b minus a, both sides of this congruence equation, then this implies a q of b is congruent to 0 mod b. Well, what does this mean? This means that b is a solution or a root of the q of x congruent to 0 mod p. It does have a solution. Now, since the degree of the q of x mod p is k, this implies the q of x congruent to 0 mod p has at most k solutions. And this in itself implies that f of x congruent to 0 mod p has at most k plus 1 solution. That's at most k plus 1 solution. And those solutions are the original one, which is x equal a, or a, together with all those solutions coming from the q of x. I may actually add to this, just to emphasize here, what we have b is a solution for this, and this is true, and which actually we can say a little more in here. What we can say a little more that for any solution of f of x going to 0 mod p, so every solution to this is a solution as far as it actually does not equal, even, well, when x equal to any solution does not equal to a, any solution not equal to a, all right, of f of x, it would produce is a solution to q of x congruent to 0 mod p. This is implicitly the way when we chose b, all right, it was any solution that's not congruent to x. So this is, what this one is saying. So, and now, since the degree of the q of x is k, by the induction hypothesis, q of x has at most K solution plus the extra solution x equal A, then we have at most K plus 1 solution. All right. An important corollary to this is the following. Well, actually, this is where we will be using this extensively. The corollary. Again, let's assume we have a prime. A prime. And we're going to let D be a divisor of B minus 1, then the polynomial equation x to the D minus 1 congruent to 0 mod B. This has exactly D minus 1, D solution, sorry, has exactly the incongruent solution, distinct solution. All right. So let's go ahead with the proof. Let's start with D being a divisor of B minus 1 plus B minus 1 is equal to KB for some integer K. Surely the integer is going to be positive integer, right? Because B minus 1 is going to be, a positive integer, and so that's what it is. All right, and now we're going to consider this. So we're going to consider this. And this is equal to x to the power k d minus 1. And we can write this one as x to the power d to the power of k minus 1. I want to factor this, and this factors into x to the d minus 1, and then x to the d k minus 1. All right, and then plus x d k minus 2, and so on, up to x to the d k minus k, which is 1, and plus 1. All right, so in general, this means this one is equal to x to the d minus 1 times, well, this one actually f of x. Of course, where f of x equal the second polynomial, k minus 1 up to xd plus 1. And since the coefficient of this is equal to 1, okay, f of x is of degree d times k minus 1. All right. Now, and of course, all this has integral coefficients. Let's count the number of, by Lagrange's theorem, okay, the congruence equation f of x congruent to 0 mod p has at most d times k minus 1 solutions, or the k minus 1, this is equal to, let's substitute for, this is dk minus d, but dk is equal p minus 1 minus d. All right? So in other words, you can say that yes, f of x congruent to 0 mod p has at most p minus 1 minus d solutions. All right. Now, let's go back in here. Remember that we have xp minus 1 was minus 1, so this is equal x to the d minus 1 times f of x. Yes, wait, this is congruence, 0 on p. You know that this congruence x p minus 1 congruent to 0 mod p has p minus 1 incongruent solution. This is by Fermat's theorem. Okay? This is by Fermat's. So this is the example we looked at. Okay? This congruence has these many solutions. All right? This means that so let's take a solution that x equal a be a solution to this xp minus 1 congruent to 0 mod. And I want this, now remember that this is a solution to this part, not a solution, because the f of x, that doesn't have p minus 1, it has p minus 1 minus d, because there are some solutions in here, they are not going to be a solutions to f of x. So this one, but not a solution to f of x congruent to 0 mod. Please take what I'm saying in here. So we are taking a solution, x equal a, we put it a, to be a solution for the x to the p minus 1 minus 1 congruent to 0 mod p. This is guaranteed by Fermat's theorem, all right? To have p minus 1 solution. So I'm taking one that is not a solution of the f of x. Okay. Now, what does this imply? This means that we have, let's go back and substitute. Here is our congruence equation. Our congruence equation is this, mod B. So you're going to substitute in here. So we have A or B minus 1 is congruent to A to the D minus 1, then F of A. I know this one is congruent to 0 mod B. All right, so we have a congruency. Also, we have the F of A is not congruent to 0 mod B because it's not a solution. All right, so it makes that the F, the greatest common divisor of F of A and B is equal to 1. Right? So we can take this and we can divide by F of A, both sides, and this implies x to the d, A to the d minus 1 is congruent to 0 mod b, which make A x equal A is a solution. To x to the d minus 1 congruent to 0 mod b. All right, what does this mean? That for every solution x equal to A to the original equation, the x to the b minus 1 congruent to 0, this will correspond to a solution to x to the d minus 1 congruent to 0 mod b. So what does this tell us? That this x so therefore, x to the d minus 1 congruent to 0 mod b has at least these many solutions. The original equation that x to the b minus 1, it has b minus 1 solutions. And we're going to take those solutions for the f of x, which was, let me see, the f of x, the solution of it is b minus 1 minus d. All right? So this one has at least the total number of solutions take out the solution for f of x. That's what we have shown in here. And when you do this one, then this is equal to d. Now this is at least, not, we don't know that if every one is going to be, incongruent, different, mod d at least. So this one, not mod b minus 1. So this one has d solutions. So at least these many solutions. Moreover, since the degree of x to the d minus 1 mod p is d, then by Lagrange's theorem, then x to the d minus 1 congruent to 0. Actually, we put in here mod congruent to 0 mod p. All right, mod p has at most d solutions. Now, these together has at least dissolution and at most dissolution. This implies that x to the d minus 1 congruent to 0 mod p has exactly dissolution. All right, so it has exactly dissolution. All right, let me move on to the a corollary to Lagrange theorem. Another corollary, basically, is a proof of Wilson's theorem. Now, remember that we proved this back in chapter 5. And here is another proof. So if you are asked to prove Wilson's theorem, you could actually present either one of these proofs. All right, here is the corollary. And this is Wilson's theorem. Now, let's record what Wilson's theorem is saying, that let E be a prime. Then E minus 1 factorial is congruent to negative 1 mod. Actually, Wilson's theorem is if and only f. But the original theorem by Wilson is going this way, proving that for any prime, e minus 1 factorial is congruent to negative 1. Then later on, it was proved that also if this holds for an integer, p or n, if you want to change it, then it must be a prime. So it's an f and only f. But this is what we would like to do this direction, that for a prime, p, this congruence relation actually holds. And the proof we're going to use, again, Lagrange's theorem, which means we're going to create a polynomial. So I'm going to let f of x equal x minus 1, x minus 2, up to x minus p minus 1, minus x to the p minus 1 minus 1. We're going to define this polynomial. Of course, it has integral coefficients. And if I multiply it out, all right, then I'm going to get, there are a p minus 1 x's in here. 1 x's. All right, so when I multiply it out, we're going to come up with xp minus 1, plus, of course, other thing, all right? And then we're going to have a minus, go in here, then we have x p minus 1, then a plus 1. Now we're going to see that the x to the power p minus 1 and this one cancel out. And what we left with is actually the highest x is going to be p minus 2. And plus, other coefficients, and maybe, we could have actually a coefficient in here, and we call it a p minus 2, then a p minus 1, minus 3, x p minus 3, and so on, up to a something. So you multiply it out and so on, and with that similar terms, you're going to come up with this. And so we have this, where all these AIs, of course, are integers, positive, negative, the 0 also. And also the degree of this, and the degree of f of x is p minus 2. All right. Now, we're going to show that, claim that f of x is actually has b minus 1 solutions, all right? So here's the claim. F of x is going to 0 on b as x equal 1 to up to b minus 1 as solution. And all of these numbers are, of course, incongruent. All right? And to do this, we actually substitute. Remember that we have f of x. All the multiplication here, we're doing it just to see the degree of this is e minus 2. Okay? So let's go back to the original form. Minus x e minus 1. All right, so you take x equal 1, then we have f of 1 is equal 1 minus 1, then 1 minus 2, 1 minus p minus 1, minus 1 to the p minus 1 minus 1. Of course, all this product is going to be 0 because there is a 1 minus 1, and this one is also 0. The x equal 1 is a solution. Now, let's take x equal to 2. We similarly we have x equal to the up to e minus 1. Let me actually put in here to make sure that we do I won't do it for 2. Okay, here we're going to think of this as congruent to 0. Or it's not that regular equation, just a congruence equation. For this one, it becomes 0, but for x equal to, let's look at x equal to 2. Okay, x equal to 2. So we have f of 2 equal 2 minus 1. Then 2 minus 2, it's going to make all of this 0. And here it's going to be actually 2 to the power b minus 1 minus 1. Now when we take congruence, so this is equal to 0. Okay, but 2 to the p minus 1, this one is congruent to 0 by Theorem's theorem. All right, by Theorem's theorem. Of course, I'm taking p here to be a prime that is bigger than actually 2. Okay, for 2, it is trivial to check the the congruence relation directly. You don't need any theorems, basically. All right, so similarly for the 3 and so on. So these are all solutions. Now we have, this will contradict Lagrange's theorem. Unless really this polynomial is not what it's supposed to be, sort of. All right, so therefore, what we are saying, the conclusion of the claim that f of x congruent to 0 mod p has p minus 1 incongruent solutions in solutions for mod p contradicts this contradict Lagrange's theorem. Unless the coefficients that a, b minus 2, all of these actually are congruent to 0 mod p. All right? So this means that the f of x is going to be actually equal to or congruent to 0, is identically equal to 0, basically, for any x in Z. All right? So for example, for x equal to 0, this implies that we have the substitute in by substituting x equals 0 in this f of x, which is equal x minus 1, x minus 2, x minus p minus 1 minus x to the p minus 1 minus 1. So substituting this one, 0 for x, implies that 0 minus 1, 0 minus 2, and so on. 0 minus p minus 1 minus 0 to the p minus 1 minus 1. So this is actually is going to be congruent to 0 mod p. All right, so what we get in here, we get negative 1 times negative 2 times negative p minus 1. This one becomes plus 1, minus minus, plus 1 is congruent to 0 mod p. We have negative 1 to the p minus 1, that's how many negative 1s we have. Then we end up with p minus 1 factorial. And then this is congruent to negative 1. We take the positive 1 to the other side. And this is mod p. Now, again, we are assuming that the prime p is odd. And this makes the negative 1 to the p minus 1 becomes even. So this becomes positive 1. And this proves that p minus 1 factorial is congruent to negative 1 mod p. All right. So again, this one is actually equal to 0, or maybe actually I should have said this one is congruent to 0 mod p. It's an identical mod p for any x in Z. All right, for any x in Z. It's an identity. It's identically equal to 0 to the polynomial. All right. Let me see here how much we have. All right. Now we're going to come to basically the main theorem of this section, Theorem 8.6. We state the theorem, and then we're going to look at an example to illustrate the technique that we're going to be actually using in the proof. Okay, we've done this before. We looked at an example before we get the general proof. And since the example the proof we get is kind of constructive proof, then if we look at an example, hopefully we'll understand the proof a little better. So here's the theorem. .6 sees that f e is a prime number. And really we are interested in p being bigger than or equal to 3. All right? But even this works for 2. And d is a divisor of p minus 1. Then there are exactly p of d incongruent integers mod p of order d. Of course, mod also p. Concept of order mod. All right. So this is the theorem. Again, I'm going to be looking at an example to illustrate the technique that we're going to be using. Okay, in the proof. Okay. So here's the example. I want to take p to be 13. And then we have p minus 1 equal 12. And the divisors of the 12 are d, which is 1, 2, 3, 4, 6, and the 12. Now, we're going to find, all right, first of all, the order of all the integers, all right, mod p, all right? So you're going to find the order of 1, 2, 3, up to the 12. All right? Mod, of course, mod 30. Of course, in the proof, we don't need to do this, but at least in here, so you can see what's going on. All right? So I'm going to write the orders of these. Okay, so the order of, remember this notation we use order, mod 13, or sub 13 of 1. This is equal 1. Then we have the order of 2. So I'm going to drop the 13. The order of 2 is 12. So remember, the order is the smallest positive integer. When you raise 2, you come up with congruent to 1 mod 13. So 2, you need to raise it. The smallest integer is 12 to get congruent to 1. The order of 3 is 3. The order of 4 is 6. Order of 5 is 4. The order of 6 is 12. The order of 7 is 12. Order of 8 is 4. Order of 9 is 3. Order of 10 is 6. Order of 11 is 12. and last order of the 12 is 2. Well, now the crucial step in this example and in the proof, we're gonna do a partitioning of this set. So we're gonna call this. We're gonna call it S, all these integers, and then we're gonna partition this set into disjoint subsets according to those integers. They have the same order. From S, we're going to put them on these different subsets. All right, so we're going to let S equal 1, 2, up to 12. Then we're going to partition S into subsets for each divisor D of 12, all right, as follows. We give the general construction, so we're going to call this subset S sub D. So this consists of those integers k in S from 1 to 12 that have the order, all right, sub 13 subprime of k is equal to D, and of course the greatest common divisor of k, and let me see in here, make sure they do this one. Yeah, k and D is equal to 1. That are relatively prime to 3. All right. So in our example, okay, so we're going to look at first of all the divisor 1. It's going to contain only one integer that is of order 1, that is 1. All right. So we have S1 consists of 1. S2, those integers they have order 2, and the integers they have order 2 is only 12. All right. So 12 is in here. All right. And then we have S3. Let's see in here. I'm going to do something. Actually, this is greatest common divisor. No, this is incorrect. I just need the order, sorry. It's the order to be. All right, S3 means those elements that have order 3. We have 3 and 9. S4, the divisor 4, and there they have order 4. There is 5 and 8. 5 and 8. Then we have S6. Try to take all this out. I have it in my notes. So we have S6 consists of 4 and 10, and S12 consists of 2, 6, 7, and 11. All right. Now we need to compare, and we're going to prove this in general, that first of all you will see that these are disjoint, because an element cannot have 2 different orders. We're classifying these according to a given order. All right, and the union of these give me all the S, all right, order and rest, because we consider for each integer, and that each integer is going to have a specific order. So it's going to fall in one of these. So that's why they give us all of that. Now, the other thing we're going to see that the number of elements in each one of these, okay, so this is equal to actually phi of 1, and S2 is equal phi of 2. Both of these is equal to 1, this is equal to 1. Then S3, it is phi over 3, which is 2. S3 has 2 elements. S4 is equal phi of 4, and phi of 4, the number that are relatively prime to 4 from 1 to 4, it is 1 and the 3, so there's 2 of them. Then S6, again phi of 6. Of course, this is not an accident, as you can tell. In other words, this is going to be true all the time. So this is 12, this is going to be phi over 12, and phi over 12 is equal to 4. Oh, so this is we're going to see in the proof. And one other observation that, which is this, okay? So in other words, we can say or conclude that the number of, so this is what we have for every d, at least in this example, which divides p minus 1, which is in this case 13 minus 1, which is 12. We have the S sub d is equal phi of d. All right? Now, we're going to denote the number of elements in each one of these subsets by the Greek letter psi of d. All right? So in here, we're going to see that psi of d is equal to phi of d. Okay, so this is true for every divisor. All right, one other claim that here's the next, and we're going to prove this is, of course, in the theorem. S sub d, we can characterize it by a to the power of k such that the order sub 13 in this case of a is equal to d, and this is where we need the greatest common divisor of the k. Let me put actually a different letter in here. Let me put R in here. And d is equal to 1. And the R ranges between 1 and d. All right? Now, this is not very hard to see, at least for in our example. We have, this is just 1, there's nothing there. We look at S3. S2 is also is only equal 1 element in here. S2 is equal to 12, so there's nothing to show there. I mean, we don't need any other powers. Now, S3, it was the 3 and 9, which is the 3 and the 3 squared. So sort of similar. But S4 is 5 and 8. So it's going to be 5 and the power of 5, which is 5 to the 3rd. Or you can write it 8 and the power of 8, by the way. And S6, you're going to see this is 4 and 4 to the 5th. And S12 is going to be 2, then 2 to the 5th. This gives you 6, 2 to the 7th give you 11, and 2 to the 11th give you 7. So this one is equal actually 6 for mod remember 13, and this one is equal to 11, and this one is equal to 7. All right, not mod. Okay, all these are mod 30. Now, this is why we're going to see that why the order of this is equal to, or the number of elements of it is equal phi of d. It actually follows from the S of d is equal to this. Remember this one, once this one is saved, that S of d is going to be all these different powers of A. Okay, it would be 1 when we have the A itself. And these are relatively prime, okay, to d. And this means that the order of this is equal to phi of d by definition of phi of d. Okay? So this is where we're going to see this in the proof. All right, now we are ready to do the general proof. So this is a proof of theorem 8.6. So I'm not going to restate the theorem. I'm just going to go ahead and look at the proof. All right, so we're going to start with, as we did with the example, that S consists of 1, 2, up to p minus 1. Now, for each divisor, d of p minus 1, we define S sub d to consist of those integer scale S is from 1 to p minus 1, such that the order of k mod p is equal to d. And we're going to let C of d to be the cardinality of this. So in words, this means this is the number of integers k where k is between 1 and p minus 1, whose order is d is equal to. Oh, so I want to give it descriptively. That's the way it is done in the book. All right, so our objective is again to show that C of D, so this is our objective. At the very end is to show C of D is equal to 50. That's what the theorem is saying, okay? It's just stated in terms of these notations that we introduced. All right. Now we have, these are some of the things we need. Now remember that the order of any element is divisible by phi of p minus phi of p, okay? So each, the order of each k between 1 and p minus 1 satisfy this. P of K divides phi of P, which is P minus. And this, of course, means that the orders for these elements definitely they're going to be less than or equal P minus. Okay. Now, and this in itself implies that the S sub D, okay, these sets subsets S sub D partition S. All right? And this means that when we are adding the order of each one of these, or the number of elements in each one of them, D divides P minus 1, which is the same as D divides P minus 1, or remember that the S of D, the number of elements, we denote it by this Greek letter, C. Okay, and this is equal to P minus 1. Because all the elements in S, there are a total of P minus 1. All right, also we have by Gauss's theorem, (7.6), the summation of phi of D, D divides P is equal to P minus 1. So in other words, when you have putting both of these together, this implies that the summation of D divides P minus 1 of the XC, which counts, number of elements for a given order, the different orders, is the same as Euler's phi function, P minus 1. So two different ways of counting, but it turns out the total number gives us the same, which is in both cases, each one of these gives you P minus 1. All right. And this in itself, we're going to come back to it. It means that D divides P minus 1, C of D minus phi of D. So this sum is equal to 0. Eventually, what we're going to be showing that the expression inside this one is going to be actually bigger than or equal to, actually less than or equal to 0, because these are the sum of non-negative integers, and then we're going to conclude that they must be equal to each other, okay? But we will come back to this later on. All right, so at least remember this. Now, we're going to proceed to the claim that actually C of D is less than or equal. In our example, we show that equality all the way, but there are some cases we might have actually the FC is less than or equal. Means we could have some of these subsets to be empty. Okay, didn't have it in our example. All right, so here's the claim that for every D divisor of P minus 1, we have C of D is less than or equal to phi of D. All right, so here's the proof of this. If for some D a divisor of P minus 1, there is no element or there is no element K between 1 and P minus 1, whose order is D is equal to D. This implies S of D is equal to 0. And this implies that C of D is equal to 0. But P of D is bigger than or equal to 1 all the time for any D. This is true for any D. Not actually D, for any integer, so the inequality means it actually holds. So this implies that 0 is less than or equal to all right, so this is actually holds. Now let's assume it is not empty. Assume that for D divides P minus 1, there is at least one element, one number, integer. Let me call it A. Where A is again between this such that the order of A is equal to D. And this means that the A is going to belong to S sub. All right, so this one, we have this. Now we're going to look at those powers, which we showed that actually SD is going to be some powers of one single element. I'm going to consider the integers a squared a to the power actually d. And this is, of course, is equal to 1. First of all, these integers, integers are incongruent mod p and more, and they satisfy the congruence equation x to the d minus 1 congruent to 0 mod p. Now let's see why is that, okay? Any one of these, it has the form x to the k. Since a to the k to the d is equal. Let me actually do this. For k 1, 2 up to d, we have x, a to the k to the d is equal a to the d to the k, and this is 1 to the k, or congruent 1 to the k, and this is congruent to 1 mod. So note for each one of these is actually a solution, and they are incongruent. So this means there's no others. Okay, by the corollary, to Lagrange's theorem, these are the only solution to x to the d minus 1 congruent to 0 mod. They are all incongruent, so they have, how many of them we have? We have actually d solutions in it. All right? And since also the degree of this is d, then this is f. Now I want to show that, in fact, that's the last thing. Here's that the claim actually SD is equal to, we observed this in the example that all of these are actually the elements of a state. Now we want to actually show this. So this is SD is, remember the SD are the elements from 1 to b minus 1, that, you know, the divide that they have for each divisor. D, we consider S sub D to be the elements from 1 to b minus 1 whose order is D. So this is what S sub D. And I'm going to show that this is also the same as these powers. Okay, a to the k such that the greatest common divisor of k d is equal to 1. And we have the, of course, the k is between 1 and d. Of course, from what we have shown it here, we have this actually does consist of, so all of these integers, they are going to be is contained. Let me say this. From what we have shown, we have this set actually for all the k in here, for all k, so in particular for which satisfy this condition, okay, greatest common divisor equal to 1 with, again, k between 1 and d. This is contained in S sub d. Each one of these, we have shown that it has actually order. All right, now let's go the other way around. Now we're going to let B be an element in S sub d. And this implies that B is a root of x to the d minus 1 congruent to 0 mod. And this means that B is going to be equal a to the k for some k between 1, and D. Now let's look at the order of this. So this is the order of A to the K. And we have a formula that gives us the order. Section 8.1, it says that this is the order of A divided by the greatest common divisor of the exponent and actually the order of A, and the order P of A. And now the order of A is equal to D, and this one the greatest common divisor of KD. Now, the order of P, since it is an SD, is also equal to D. So this is equal to D. Now, when we put this D here, so this equation holds if and only if actually the greatest common divisor of K D is equal to. All right, so in other words, those P, which are of the form A to the K, they must satisfy the greatest common divisor of K and B is equal to 1. And that is what the S of D is going to be. All right. So to summarize, so therefore, we have SD consists of A or K such that the order of, how are we going to say this? Actually, such that the order P of A is equal to D, and greatest common divisor of K D is equal to 1. Or now this implies that SD, which is equal to C of D, consists of, now let's do it in here. The counting in here is actually based on K such that they satisfy this. This order is just telling us, that specify we are in this subset. And this is gonna actually is equal to phi of D. All right. This is equal to D. So in general, together with we have C of D is going to be less than or equal to phi of D. Because there is the case where if S of D is empty, then we have this. And this implies that C of D minus P of D less than or equal to 0. And this is again for every D, a divisor of B minus 1. But we have this summation, D divides P minus 1, C of D minus P of D is equal to 0. So if this sum is 0 and each one of these elements is less than or equal to 0, the only way both of these two, the equation and the inequality holds, implies that this must equal to 0 and this make these are equal to each other. All right. Now, a corollary to this is when we take d is equal p minus 1. Okay. A special case is if the divisor d is equal p minus 1. Then we have the following corollary. If p is a prime, then there are exactly phi of p minus 1, that's phi of d. All right, integers or of order or incongruent integers rather. Mod p with order equal to p minus 1 or equivalently phi of p. This is equivalent to saying that p has phi of p minus 1 primitive roots. Because primitive roots are those integers, they have order p minus 1. So this is exactly what this one is saying, just it says there. So it doesn't only tell us that, primes has primitive roots, it's also actually give us a count for the number of primitive roots there are phi of p minus 1. Now, a few things left, which I will try to fill in here. The first one is, again, another proof of a theorem that we proved in chapter 5, and a few comments about the actually primitive roots. So let me start with the primitive roots, the comments. You see this corollary, it tells us, and this is followed from the theorem, right? Tell us that that if we have a prime, then there are phi of p minus 1 primitive roots for this prime. However, it does not tell us how to find primitive roots. It's not constructed. I mean, we don't know how to find those primitive roots. So if you want to find the primitive roots, either you use brute force, okay, by taking integers and trying to find the order of this mod p, till you find an integer that has order p minus 1, and then you find the primitive roots. There are some tables that has been prepared for that list, different numbers and their primitive roots. Also, you could use those. Nowadays, with computers, of course, we could actually generate some primitive roots for some polynomials using some of the algebra computer system that actually does handle these kind. Now, when you look at either tables of primitive roots, you find that the smallest primitive root happens to be 2, and it occurs very, very often for many of the primes. However, it is not known whether there are infinitely many primes that their smallest primitive root is 2. So this is it's a conjecture, means it's not known. Also, if we even change 2 to another number, okay, it is not known whether there are infinitely many primes of of a certain value for a primitive root. Gauss conjectures that 10 for the integer 10, there are infinitely many primes. They have actually in other words, 10 appears as a primitive root for infinitely many primes. But actually, this was never proved. In 1927, the mathematician Emil Artin actually generalized Gauss's conjecture to the following. This is called Artin's conjecture. This was given in 1927. And it says the following, all right? The integer A is a primitive root of infinitely many primes if A does not equal to plus minus 1 and A is not a perfect square, not a perfect square. A very famous conjecture by Emil Artin, all right, and still unsolved. There are some more information about, Emil Artin's in the book, and a little bit of history of primitive roots and so on. So I suggest if you would like to take a look at this, it's on page 157. So page 157 has a little more information about this. So I'm going to go back to prove one other theorem, and that's going to be of interest to us in the next chapter, chapter 9. And this is a specific type of quadratic congruence equation. It's solution when it has a solution. So I'm going to do this, and this will be it. So this is theorem actually 5.5. So we're going to do a proof on, using primitive roots, basically, 95. So this goes back to this. And this is a way that it states that let P be a prime. Then the quadratic congruence x squared congruent to -1 mod p has a solution if and only if P is 2 or P is congruent to 1 mod 4. it's a prime of course like this. Or this is equivalently saying that P it is of the form 4k plus 1. All right. So let's go actually backward in here. So let's assume that because if P is equal to 2, then x equal 1 is a solution to x squared congruent to -1 mod 2. Just by substituting for x equal 1, we get 1 is congruent to -1, because that's going to give me 2. All right, and that's divisible by 2. All right, so let's go ahead and assume that P is congruent, means that 1 mod 4. And this implies that 4 is going to be divisible by P minus 1. All right? And this implies by theorem 8.6, there is an integer let's say A, with whose order is 4. And what does this mean? This means that A to the 4 is congruent to 1 mod B. And in fact, 4 is the smallest, all right, exponent that satisfies it, all right. Now, let's go ahead and work with this congruence relation that we know it is true, it holds. So from here, we conclude that a squared minus 1, well, let me write it as a to the 4th first. A to the 4th minus 1 is congruent to 0 mod b. Again, factoring the left-hand side into a squared minus 1, a squared plus 1 to 0 mod. So this means that either one of these is going to be congruent to 0 mod. So this implies, let me actually make it as a divisibility relation. And since P is a prime, it's going to be divide either one of these, or P divides a squared plus 1. And this implies, again, a squared is congruent to 1 mod b, or a squared plus 1 is congruent to 0. We make this is, yeah, this is congruent to 1. Means actually a squared minus 1 congruent to 0 is like this mod. But this is not true because this does not hold, since the order of A is equal 4. So we cannot find a smaller exponent to make this congruent to this. So in other words, that is not going to happen. So it means that the second congruence actually is the one that's going to hold. Right? So this means that a squared plus 1 congruent to 0 mod b, this. And then it implies that a squared is congruent to negative 1 mod b. Therefore, x equal a is a solution to x squared congruent to negative 1 mod b. And that's it. Now, the other direction, the direction going this way, this is the same as, it has nothing to do with this theorem, basically. The same as the proof in Theorem 5.5 on page 95. So it's not any, it's the same thing, means it just follows from that. All right, so I'm going to stop right here for this section. It is longer than what I thought. So that's what it is.